Hi everyone, Christian Aparicio here to give you another tutorial with Nastran Solution 200. This tutorial is going to be focusing on how to perform an optimization for buckling analysis. Now, this problem was inspired by an engagement with when I had an interaction with a student. This student was working on an aircraft wing model. This individual was focused on improving the buckling factor of the model. Now, what made this problem a little tricky was that the student was encountering negative buckling loads. So in this tutorial, I'm going to explain how to handle negative buckling loads when you're performing optimization. Here, since we're doing optimization, we're interested oftentimes in minimizing the weight of the structure. So here you can see that at the beginning, the design has a mass of 15.12 kilograms. And then towards the end, we have an improved design that has a mass of 2.35 kilograms. Now, just a quick explanation of how the model is configured. One end of this box section, if you will, is fixed on one end and then free on the other end. We have this combination of loads here at the tip. This example also yields a negative buckling load and a positive buckling load or buckling factor here. Know that what a negative buckling factor means is that if the load were to be reversed, that would cause a buckling. So for example, here the load is going upwards. So the buckling factor is 242.19. But if the same load were to be reversed, hence the negative buckling factor here, it will cause buckling on the other side of the section of the structural member. So later on, I'll explain how to handle this. We also see the same thing when we're dealing with the other load that goes in the horizontal direction in the positive X direction. You can see that for mode 1, we have a negative buckling factor, and then for mode 2, we also have a positive buckling load factor. So now, what's our problem statement? So the problem statement should always be the first thing that you start off with when you're performing optimization. Take time to sit down, get a piece of paper, and write down what you want to vary in your Nastran model. What fields of the bulk data entries you want to modify. Also specify your objective. What do you want to minimize or maximize? Also specify your constraints, the bounds of the constraints, and so on and so on. I recommend this because when you use the web app to configure all of this, this problem statement is going to make things a little easier for you later on. So here for this particular model, all the thicknesses, all the walls of this member are defined by a thickness on the P shell entry. We want to vary the thickness between, or rather have a lower bound of 0.001. Now for the objective, we want to minimize the weight. For the constraints, we want to constrain the von Mises stress of the top and bottom fibers of each wall. We want to make sure that the stress, or the von Mises stress, does not exceed a value of 2.76 times 10 to the 8 value, or units of stress. Now for the design constraints, remember, we're dealing with both a negative and a positive buckling factor. How do we do this? What we're going to do is we're going to define the equation constraint as follows. We'll let B1 correspond to the buckling factor of mode 1 and let B2 correspond to the buckling load factor of mode 2. Here, what we're going to say is that we want to constrain the absolute value of the buckling factor. So regardless of whether the buckling factor is positive or negative, this is going to help us keep the sign consistent. So then here, our final bound, if you will be keep the buckling factor above 1. And then one other thing, here we're performing what's called a multidisciplinary optimization. When you configure your BDF file for buckling, the first half of your subcases are dedicated to statics analysis, and then the second set of subcases are dedicated to the buckling subcases. Here, the von Mises the von Mises constraints are applied to the static subcases, so hence we have the checkboxes marked here. And then the buckling factor constraints are applied to the buckling subcases, hence these bottom right checkboxes are marked. And then before starting the tutorial, I just want to point out that for anyone that has a question on optimization with Nastran, this could be regarding Nastran Solution 200. This can be related to machine learning with Nastran. You can contact me at this email address with any questions or comments you might have. You can be a student or a professional engineer, and I also welcome questions from these groups. Also, professors, you're welcome to contact me at this email address. Now, if you're dealing with a different finite element analysis program, you can also contact me. If you have other projects related to structural or mechanical optimization, you can reach out to me. And if you want access to the web app we use today, you can contact me at this email address. Now, let's go ahead and start the tutorial. One thing I like to do with any tutorial is I like to have a clean downloads directory. You're going to be dealing with a lot of files, and just to avoid confusion with all of these files, I like to delete or just relocate these files temporarily. Now, to start off with, let's go ahead and open the web app as you see here, and let's open the user's guide. The PDF file that describes this finite element model has already been created for me. I've already used Patran or MSC Apex or your own finite element program to create the FE model. But what we want to do is just download this PDF file that's available online. So let's go ahead and download it here. And so if we open this PDF file, you'll see that it's already been configured for solution 105, which is buckling. All the subcases are defined, all the elements, nodes, and so on and so on. That's already been defined. So I've done this before this tutorial. Let's now open the size web app, and let's go ahead and import or upload the PDF file. So we'll click select files and select this PDF file and select upload. Here I get a list of all the bulk data fields that I can set as variables. Here I want to select the thickness field as a variable, and the lower bound is going to be 0.001. Let's go ahead and make sure that that corresponds to my variable section here. And now let's go ahead and focus on the objective. Here I want to minimize the weight. So out of all the responses available, I want to set the weight as a response I want to minimize. So that's corresponding to the R0 response. Let's go ahead and move on to the constraint section. Here, let's change the analysis type. So I'm looking at responses from statics. Here, I want to constrain the stress response. So let's go ahead and create two stress responses. I want to track the von Mises stress for the top and the bottom fiber of the P shell, and I want to do this for P shell 1, and then the upper bound is going to be this value of 2.76 e or times 10 to the 8. So let me put that here and here. And now let's go ahead and mark this checkbox, create equation constraints. Remember, we're dealing with both negative and positive buckling factors here. What I recommend doing is I recommend taking the absolute value of these buckling factors. So here, let's first create our buckling factor responses. So we'll click the plus icon for buckling eigenvalue / factor. We'll say buckling mode 1 and buckling mode 2. So now we have responses B1 and B2 corresponding to the buckling factor of mode 1 and 2 respectively. Let's go ahead and click add equation constraint, and this is where you can type in absolute value or ABS of B1, and then we'll do the same thing for ABS B2. And here we want to make sure that the buckling factor is greater than 1. Now, one thing to keep in mind, suppose that I make an error when I define the equation constraint. And note that the equation constraint is a combination of two things. It's a combination of a DRESP2 entry, a D equation entry, and a D constraint entry. Also, there's a DRESP1 entry involved. If I make an error, the web app immediately detects the error. and I can correct the error here. You do not have to wait until the end when you run Nastran to finally have an error during the optimization. Here, the web app tells you when there's an error. Then as you update the equation, it tells you, and then you can update the equation. It immediately updates whether or not the status is okay or not okay. This is a big time saver, and I wanted to point that out right now while doing this example. Now, let me look at the problem statement and make sure I've defined the weight, the von Mises stress for the top and bottom fibers of the P-shell sections. Let's see, I've defined my buckling factor constraints for mode 1 and 2. Let's go ahead and make sure I've done everything here correctly. And the von Mises stress, E8, E8. Okay, now for the subcases. Now remember, the first two subcases correspond to statics. If you look at your BDF file, look at the case control section, you see that there's no indication of statics, but it is. If you look at subcase 3 and 4, here you see that it's denoted by the stat sub entry or control command. This is indication that these are buckling subcases. So we have to differentiate the subcases here. The way we do this is we click options, we click use multidisciplinary optimization, and then here we say that the first subcase is statics, the second subcase is also statics, the third and fourth are buckling subcases. For the von Mises stress constraints, those apply to the subcases 1 and 2, and then the buckling factor constraints correspond to the 3 and 4 subcases. And let's see, there's one last thing I wanted to point out, and that is the settings section. I've noticed that frequently when you're performing buckling optimization, the optimization is better helped in some cases if you use what's called the truss region. Remember that the Nastran optimizer has various configuration settings for the optimizer. A lot of tolerances for conversions and things of that nature. The truss region, what that does, it triggers the automatic modification of these tolerances, if you will. So you don't have to be manually modifying these settings by yourself. Nastran would do this by itself when you turn on the truss region. For some optimization cases, this yields a faster optimization. For some optimizations that have problems, you can turn on the truss region and it will help the optimization. So I recommend trying your optimization with and without the truss region on just to see if it's better or not. It's definitely worth taking the time to see if it does help or not. Now, once I've done this, let's go ahead and click the exporter and click download BDF files. And let's go ahead and extract the contents of the zip file. Inside is the original BDF file, but now it's been configured to solution 200 to perform the optimization. It has a pointer to the objective entry. So here the DESOBJ is pointing to DRUS 1 with this identification number. It's got the analysis entry or control command saying that this is a static subcase. The next three subcases, or 3 and 4, are buckling subcases. So we have buck here. It's pointing to constraint groups, ID sub this number, and so on and so on. If you look inside the design model BDF file, this has all the entries for the design variables, for the objective, and the constraints. And everything is in here for you. You don't have to modify anything. We'll go ahead and click Start MSC Nastran, which will start the optimization. During the optimization, I get a status update. This just gives me an idea of where the status is at in terms of design cycle numbers. If we look at it right now, we are currently in the initial design cycle number. And right now we're in design cycle 2. So we'll just let this run for a few moments. And while this is happening, let me point out in the web app the error detection error detections rather. Let's go ahead and suppose I made an error on the equation constraint. Here I forgot to complete the expression for the equation constraint. If I go back to the exporter, I get an error. It's important to resolve these errors before you run your Nastran optimization. If you go forward with this optimization as it's configured, you are most likely going to encounter an error during your optimization. Every finite element program, every optimizer is going to have this challenge. You're going to encounter an error, but the web app catches these errors for you before that happens. If I go back and I correct the issue, actually here I can just click the link, jump to table. It takes me to the table. I modify it. I go back to the exporter and the error is gone. So now if I go forward, the optimization is more likely to succeed. Now, let's look at what's happened here. We have the message run terminated due to hard convergence, but we should really be careful and look at the objective and the max normalized constraint plot. Our objective was to minimize the weight. Has the weight been minimized? Here it's 15.12 at the beginning, and at the end it's 2.34. So yes, the objective has been minimized. Is the final design satisfactory? Does it satisfy all the constraints? You know that it satisfies the constraints when the normalized constraint value is negative. Negative means it satisfies all the constraints. Positive normalized constraint means it's violating the constraints. Here, after design cycle 12, the normalized constraint is negative. That means the constraints are satisfied for design cycle 12. Here, you still have a negative constraint, and then at the very end, you still have a negative constraint. So 12, 13, and 14 yield designs that satisfy the constraints. So this has been a successful optimization because the objective has been minimized and the normalized constraints are negative at the end, which means you satisfy the constraints. You'll notice another thing. Here, the design cycle numbers are denoted by this R, 1R, 2R, 3R, 4, 5R, and so on and so on. This is a result of using the trust region. What happens after the initial value, when you have the trust region, the optimizer tolerances are modified for you automatically. Here, after design cycle 1, it's found that the tolerances were not successful after design cycle 1. So those tolerances are rejected. The tolerances are modified again. A second design cycle is performed, and again, that design cycle was not good, so the tolerances are rejected again. It happens again for the third design cycle, and then after the third design cycle, it modifies the tolerances again until you get to design cycle 4. So design cycle 1, 2, and 3 are rejected. That's not part of the optimization path. So you go from the beginning, the initial, to the 4. 5 and 6 are not good, so those design cycles are rejected. So you go from 1 to 4, or the initial to 4, to 7, to 10, to 12, 13, and 14. 8, 9R, 11R, you can just ignore those rejected design cycles. Those don't even come into play. Again, this is because of the trust region. The trust region will try to modify your optimizer settings. If it's good, it continues on. If it's bad, it rejects the design cycle and it tries again. Here, one thing that's worth looking at, you might be asking, how do we know for sure that the buckling factor is good? What you can use is this other web app called the responses web app. If I open the F06 file, the F06 file will have a section called responses and design model. This is a table that tells you what the values were for the responses. Remember that B1 and B2 correspond to the buckling factors of mode 1 and 2. So let me go back here. So we want to confirm that these buckling factors are greater than 1. So once we open the responses web app, I'm going to select the F06 file and upload the F06 file. Here we want to look at just maybe B1 for now. we'll see that at the very end, the buckling factor is -1. Remember, we were tracking the absolute value. So for B1, it's right at the edge of the bound, which is 1. The absolute value of B1 was 1, but here it's -1, which makes sense. Here, B2, again, it's 1. So this is good. That means that our final responses, or our final buckling factors, are right on the bound. So this is giving us confidence that we have successfully improved this design. And remember that our starting buckling factors were -242 and +242, but our final buckling factors were -1 and 1. So we have successfully completed this optimization. Again, this example started off from an engagement with a student. The student was interested in performing a buckling optimization for an aircraft wing. The student quickly discovered that there were both negative and positive buckling load factors, so I worked with him on how to address that case, and the outcome of that work is this tutorial. So I hope this tutorial helps you when you perform buckling optimization. Now, there's one last thing to do. If we look at the original BDF file, we have to update the P-shell1 entry with the updated thickness. So here, P-shell1, we started with the value of 0.001. What you can do is you can look at the variable change. It started off with 0.01 actually, and then it ended off with 0.00155. What you can do, you can manually change the value here if you want. Here, 0.01, I forgot what it was, 0.0015. So you can, if you really wanted to, you can come here and modify this manually. There's an easier way. The first way is by opening up the PCH value, copying all the lines, and pasting it here. That's the first way. This way is easy for this example because there's only one entry, but what happens if you have 100 entries? What do you do here? What you can do is you can go back to the size web app and open what's called the PCH to BDF web app. Here you can select the PCH file. You can select the BDF file you want to update. Here it's detected the new P-shell value, the P-shell entry. It's going to replace the old P-shell entry. And we'll click download. We get another zip file. And if we open the zip file, inside, if we open that file, we see that the P-shell entry has now been updated. So on the left is the old BDF file, and here on the right is the new BDF file with the updated P-shell entry. The one last thing I wanted to leave you off with, suppose that you are done with your work for today and then you start again tomorrow. How do you modify your work? You can go ahead and select the old BDF files, click upload, and then the web app will import your old problem statement, your old variables, your objective, and your constraints. If you wanted to add or remove items from your problem statement, you can do that here. If you wanted to modify your subcase definitions, you can also do that. So that's how you import your work and continue on. So that's the end of this tutorial. As always, if you have any comments, questions, if you're a student, professor, professional engineer, if you want to perform structural or mechanical optimization using Nastran or some other FEA program, you're welcome to contact me at this email address. I focus on problems related to gradient-based optimizers, machine learning, and various other optimization methods. Also, if you want access to the web app I showed you today, you can contact me at this email address. Thank you so much for watching.